Hello, AP Chemists. Welcome to our next unit, which is our thermodynamics unit. We are going to start this unit by talking about heat. Okay, before we do that, let's talk a little bit about what thermodynamics is. So thermodynamics is the relationship between chemical reactions and heat. Okay, so we're going to look at how heat affects chemical reactions. And how we can look at a chemical reaction and talk about what is happening in terms of the transfer of heat. Heat is a form of energy that we are going to measure in joules. All right, well, you'll also possibly see problems where it is measured in calories or cal. All right, but typically we are going to see our problems in joules. Temperature is a measure of average kinetic energy of atoms and molecules in a system. So, not all particles in a system are moving at the same speed. Some are moving slow and some are moving really fast. Okay, but the average kinetic energy can be measured, and that is our temperature. Okay, so as the temperature is increased, we would see more of those fast molecules and fewer of those slow molecules. That is typically shown in a Boltzmann distribution, where we have on our y-axis the number of particles, and on our x-axis we have kinetic energy. So what you see on this particular Boltzmann distribution is you see the Boltzmann distributions for 3 different temperatures. Okay, so we have a system that is at 3 different temperatures. There's some things that I want you to notice here. As the temperature increases, I want us to think about what happens to the proportion of particles with a higher kinetic energy. Okay, so if I look at what happens, for example, when I'm going from 250 Kelvin to 500 Kelvin, I see that the graph there, that the curve shifts to the right and it's lower. But what I also see is the proportion that is at higher energies is also larger. And we can kind of see that right here, right? We see that there's more particles that are higher energy in that curve. And then if I go to 1000 Kelvin, I see that there's even more high energy particles. So overall, we would say that the proportion of particles with a higher kinetic energy increases. Okay, the shape of the distribution I already mentioned. As it gets hotter, okay, as the temperature increases, we see that it starts to flatten out. So it started kind of really steep. If the temperature increases, we see that the shape flattens out. Also, as the temperature increases, we see that the peak decreases. So that's kind of part of flattening out, right? Part of flattening out is that the peak is going to be lower, but what's really important is to recognize that as the temperature increases, we have more of those higher kinetic energy particles. Okay? I also want you to notice, though, that at lower temperatures for all 3 distributions, we still see molecules there, okay, that are slower with less kinetic energy. Okay? But there's just not as many, especially as the temperature increases. All right, so now let's talk about the transfer of heat. 2 systems that are at different temperatures that are in thermal contact, so they are touching each other, will exchange energy in the form of heat. The energy lost by one system is equal to the energy gained by the other system. So here you see an initial condition, and you can see that system 1 is at a lower temperature than system 2. So system 1 has a lower average kinetic energy than system 2. So if I look at the particles in system 1, I see that they don't all have the same arrows, right? The arrows are not all quite the same size because remember it is an average. But I definitely see that system 2 on average has longer arrows because it has greater average kinetic energy. But I see that these two systems are in thermal contact. Okay, so they're in thermal contact. So when those particles from system 2 collide with the other system, energy is going to be transferred from where there is more energy in system 2 to where there is less energy in system 1 until finally they're in thermal equilibrium. Okay, so they're at equal temperatures. And we kind of see that, right? If I put my hand onto a cold surface, okay, the molecules in my hand are going to heat up that surface until they get into thermal equilibrium. Okay, so one is losing heat and one is gaining heat, but that transfer overall, whatever was lost, was gained by the other system. So the arrows represent the kinetic energy of the particles. In the initial condition, what do you notice about the arrows? Okay, we can see that they are longer in system 2. And then in the final condition, we notice that on average, the arrows are the same length. Okay, so the law of conservation of energy states that energy can neither be created nor destroyed, but it can be transferred from one form to another. Now we call this the first law of thermodynamics. Okay, so let's continue our talk on the transfer of heat. To do that, we need to define two things, the system and the surroundings. Okay, the system is the actual chemical reaction, phase change, or change in temperature that has taken place. I want you to think of this as a process. So whatever chemical process is taking place is the system. It is not, however, a physical place. So even though me drawing this name system in the box makes it look like it's a physical place, it's actually more of a process that is occurring, okay? So for example, breaking bonds and forming new bonds would be happening in the system. The surroundings are really just everything else. So this process that we are focused on is the system. Everything else is considered the surroundings. Okay, energy is transferred into or out of the system in the form of work or heat. We are going to focus on heat today. There are two types of reactions that you are going to be There are two types of reactions that you are going to have to know. There are endothermic and exothermic reactions. Both of those types of reactions are going to help us describe the enthalpy of the reaction. The enthalpy is the heat that is released or absorbed in a chemical reaction. So the heat that is released or absorbed in a chemical reaction. When heat, which I'm going to abbreviate with a lowercase q, is transferred to the system or absorbed by the system, meaning it goes into the system, the sign is positive, and the process is called an endothermic process. The temperature of the surroundings for an endothermic process decreases. Let's kind of talk about why and what we're really observing in an endothermic reaction. Remember that in an endothermic process or any process, we have our system, which is kind of our focal point, the process we are focused on, and we have our surroundings. Okay, for an endothermic reaction, the transfer of heat is into the system. So these red arrows that I am drawing are representing my heat. Okay, so heat is being transferred from the surroundings into the system. Okay, if I think about the temperature, okay, our thermometer would kind of be out here. I know it's a terrible thermometer, but it would be out here in the surroundings. Okay, so if heat is leaving the surroundings, then the surroundings are going to have a decrease in temperature. Temperature is always measured in the surroundings. You can never stick the thermometer into the system. It will always be in the surroundings. Okay, so we would always see an endothermic reaction overall get colder. Okay, so if it's decreasing, then that means that it is going to get colder. So let's draw an energy diagram for an endothermic reaction. Okay, so I'm going to draw my axes, and on my y-axis, I'm going to put potential energy in kilojoules, and on my x-axis, I'm going to put the reaction progress. So it's just the reaction is progressing from the reactants to the products. Okay, so I'm just going to arbitrarily set what my initial energy is. Okay, there's no reason why it has to be where I put it. But initially in a reaction, I have reactants. Okay, and then I form products. Now, in an endothermic reaction, energy goes into the system. So the energy of the system increases, right? Because energy is flowing into the system. So I'm going to say that my products have more energy than my reactants. The difference between the products and the reactants is how much energy was absorbed by the chemical process, by the system in the chemical process. We are going to call that our enthalpy or our delta H, which is always going to be our products minus our reactants. Okay, for a endothermic reaction, our delta H is going to be positive because our products are at higher energy than our reactants. Now, as a reaction progresses, we typically see that the curve or the energy goes like this. So we see that the energy went higher than what the products was. Now, if we think about this, we know that for a chemical reaction, bonds are broken and then new bonds are formed. So I have my initial energy for my reactants, and it took this much energy to break the bonds. Okay, so that much energy was taken to break the bonds. Now that energy is called the activation energy. Okay, that energy is known as the activation energy, and it is equal to the amount of energy that has to go in to get the reaction started, which means the energy that it takes to break the chemical bonds of the reactants. Okay, so then it asks us to describe the relationship between the energy of the reactants and the products. Okay, we see that the energy in the products for an endothermic reaction are greater than the energy of the reactants. And we already said that delta H would be positive in an endothermic process. So we've looked at endothermic reactions, so now let's do the opposite and look at exothermic reactions. Exothermic reactions are when heat is transferred from the system to the surroundings. In other words, the energy is released by the system. Because the system is losing heat, the sign for our delta H is negative. And we call this process exothermic. I like to think of it as exiting the system is exothermic. So let's look at what we have. We have our system where our chemical process is taking place, and we have our surroundings, okay, which is everything that is outside of the box. Now, in an exothermic reaction, heat leaves the system or is released, and so we would say that heat goes from the system to the surroundings. So all of my arrows there are representing the heat. Now remember, a thermometer is always in the surroundings. So if there is more heat or more energy in the surroundings, then the temperature is going to go up because the average kinetic energy of the particles in the surroundings is also increasing. Okay, so we would expect our temperature to increase. Okay, the temperature goes up because the heat is going into the surroundings. To draw an energy diagram for an exothermic reaction, I'm going to set up my axes the same way. I'm going to have potential energy on my y-axis and the reaction progress on the x-axis. Okay, I'm once again going to arbitrarily put where my reactants are going to be. So I'm just picking a point for them to start at, okay, because this is just an example. Because heat is leaving the system is going to have less energy. So the energy of the products would be less than the energy in the reactants. Okay, once again, energy has to be put in to get a reaction started. So energy has to be added to get to get a reaction started. So this is what that curve would look like. Also, the difference between the products and the reactants, remember, is our delta H, which is always products minus reactants. So in this case, if I do products minus reactants, then I would have a delta H that is negative. Okay, lastly, like I said, energy does have to be inputted to break the chemical bonds. That energy is called the activation energy, or E sub A. The relationship between the energy of the reactants and the products would be that the energy of the reactants is greater than the energy of the products because heat is lost in an exothermic reaction. Would delta H be positive or negative for an exothermic reaction? We just talked about this. Because heat is lost by the system, the delta H would be negative. So go ahead and pause the video and then fill in the summary table below. All right, so for an endothermic reaction, our sign for delta H should be positive. There should be greater energy in the products because energy was absorbed. The temperature change, these should get colder, so it goes down, or we see that it gets colder, and heat is absorbed by the system. In an exothermic reaction, everything is just the opposite. The sign for a delta H, or the sign of delta H for an exothermic reaction is negative. There is more energy in the reactants since energy is lost by the system. And we should see that the temperature should increase and it would feel to us as if it got hotter because we are in the surroundings. And the heat is therefore released. So make sure that you have an understanding of this video before coming to class because it is going to help us in our discussions that we have. Thank you and have a great day. Bye, y'all.